Hello and welcome. This is video number 3, the metric tensor in polar the coordinates. So the metric tensor is defined as the dot product of the basis of vectors. So we're working in two dimensions. So we're going to have 4 entries, right? So it's all the permutations of r and theta. So we got r theta, theta r, and theta theta. We did some of these already. That's okay. We'll do them again. So the GRR is just 1. GR theta is 0. So what's that tell us? It tells us that ER and E theta are orthogonal, right? They're 90 degrees apart. And E theta ER is 0, and E theta dot E theta is R squared, okay? So this is the metric, the tensor, which is actually the covariant metric tensor because both the indices are in the lower position. Okay, so it's 1, 0, 0 r squared. Now we need to find the inverse metric, the tensor, which is actually the contravariant metric tensor because both indices are in the upper position. Now, since this matrix is equal across the diagonal, and the diagonals are 0, it's finding its inverse is as easy as putting this over 1 and this over 1, or 1 over this, 1 over that. So it's that easy. You don't have to do anything sexy. Okay, so I just talked about this. So we have the contravariant metric tensor and the covariant the metric the tensor. So we're going to use that to introduce these new concepts. Covariant and contravariant. Now, you can represent a vector in 2 different ways. Like this with the V, the super I, and the E, the sub I. So this is the contravariant vector component and the covariant basis the vector. And what that means is that the component, it changes oppositely of the basis vector. Okay, so if this basis vector increases in magnitude, this decreases. And the other way you can do it is like this. So you have a covariant vector component and a contravariant basis vector. So this is exactly opposite behavior as this. Now, the mathematicians have to be very precise in the way they define things. So they have very special ways to define all this stuff, and we're not going to go into it because it's complicated and unnecessary for our use. Okay, so we can actually use the metric, the tensor, to raise or lower these indices. So if I have this one, if I have the V, the super I, and I want to find V sub I can use the metric tensor to do that. Okay, and it works like this. So we have this basis vector, the contravariant basis vectors. We found them above, and we also have, and I'm sorry, in video number 2. And in this video, we just found the inverse, the metric tensor, the covariant metric, the contravariant metric, the tensor, right? So these J's get absorbed and leaves only I. That's the easiest way to think about it, right? So I, in this case, is the free index. I is the free index, and J, do you see upper and lower, is the summation index. All right, so let's do it actual examples. So we have E, the lower the theta. This is the covariant, the basis vector E theta. And we want to find the contravariant basis vector, right? So here's our generalized equation. So in this case, the free index is theta. So we put I here is theta. And everywhere we see an I, we put a theta. There's a theta there and a theta there. Now, since J is our summation index, in the first case, it's going to be R. In the second case, it's going to be theta. Or it could be theta in the first case. It doesn't matter as long as it's the same. R, theta, theta. All right. Now we have all this information. That's all the stuff we have from above, right? So we dig all that out, and G theta R is 0, and G theta theta is 1 over R squared. All right. So this R takes out that, leaves 1 on the bottom. This takes out that, leaves 1 on the bottom, and we're left with this. So this is the contravariant E theta basis the vector. Now let's do ER. So here's what E covariant was. We do the exact same trick, right? So this time the free index I is R. So we got an R here and an R there and an R there. We do our summation. First time is R, R, second time theta, theta. We fill in all the stuff we know. This is 1 and this is 0, so they're the same. So the covariant and contravariant basis vectors and polar coordinates are exactly the same thing. All right, so let's go look at that on the graph. Okay, so here's where we were. We had defined in video number 2 our ER and E theta basis the vectors, who they change all over the space. ER changes direction, E theta changes direction, but E theta also changes magnitude, okay? So now we can plot those two equations we just found, and we know that the contravariant ER is the same as the covariant ER, but the contravariant E theta is not the same as the covariant E theta because it's divided by R instead of multiplied by R. So you can see that as the covariant E theta increases, the contravariant decreases, and vice versa. So it changes oppositely. You see that? So it gets longer, then it gets the shorter as that gets longer. Okay? Okay, so given all the stuff we just learned, let's prove that this is true. That this vector can be expressed as a linear combination in two different ways. And we're going to use the metric tensor to do that, okay? So we want a vector VR, ER, V theta, E theta. All right, so let's make up these components. So the contravariant, the VR component is 2. The contravariant theta component is pi over 4. I just made those up. All right, so let's put these in here, and let's put ER and E theta, which we found. So the whole thing looks like this. All right, so let's put it all together. So in other words, I'd put this EX with this one, right? That 2 wipes out half of that, but I just left it. Okay, and I put all this with this. So here is what we have. All right, now we want to find the covariant components, which we don't know. All right, so how do we do that? Well, it's the same thing we did with the basis of the vectors. So we have VI equals, now this is just a metric tensor, the covariant metric, the tensor times this, which we know. All right, so in this case, I is the free index. The first one we want is R. So VR equals GRR VR, right? So JJ is RR. I is R in every term. That's why it's called a free index. And the summation in this case is theta. All right. So GRR is 1. VR, we made that up. It's here is 2. And GR theta is 0. So the contravariant component is 2. It's the same. It's the same as the covariant. All right. Now let's find the next one, which is theta. All right. So theta is the free index. There's a theta here, a theta here, a theta here. Then we do our summation, RR, a theta, theta. All right. So G theta R is 0. G theta theta, though, is R squared. And V theta up from above is pi over 4. So this is not the same. The covariant, the vector component of theta is pi over 4 R squared. Now we can take these two things and put them together. And we found these already, right? These are the contravariant polar basis vectors. So we put all this together. Once again, we put like terms with like terms, and we wind up with this. And that looks very familiar because it's the same thing. So it's true. You can express the vector in 2 different ways, and you find all of those different covariant and contravariant components by using the metric tensor. Okay, so we're going to stop there, and in the next one, we're going to introduce a new symbol, the Kronecker delta. Very exciting.